Started. Our next speaker is Professor Sergei Dubovsky from NYU. He'll tell us about confining strings.
So good morning. The topic of my lectures will be mostly, well, it depends on how fast I will go, mostly long QCD strings. And I slightly changed the initial plan of what I'm going to cover. And the reason for that, I thought Mike Tepper will, and there are two parts of the story, and there is kind of what can be called theoretical part and what can be called experimental part. And by experiments, I really mostly mean here lattice simulations of Young-Mills theory. And I thought that the experimental part will be covered in Mike's lectures, but Mike gave a very nice general overview of lattice gauge theory, but didn't go into enough detail of data which I need for these lectures. So I will have to cover both. And so roughly the plan will be, I'll start with some theoretical considerations. Then the second lecture will look at the experiment. And then in the third lecture, with kind of hindsight from experiment, we'll come back to theory. And maybe if I will have time, I will say a few words about short strings in that part, but probably I won't have time. And well, maybe actually this change is for good because it's better reflects the spirit, at least, of how I'm thinking about this problem. And I should say, kind of, my own background is a model builder. So when I was a PhD student and my early days of postdoc, like the main spirit was those expectations that LHC will turn on and there will be new data and we'll have to work hard to explain that data. And well, nowadays, model building is almost considered synonymous to ambulance chasing. And there is a reason for that. Well, we know that LHC, maybe what LHC saw is somewhat surprising, but maybe it's not enough to give hints for doing model building. But well, in my view, at least, like good model building is when you start with some theoretical principles, you try with the models which realize those principles, you look at the data, confront you, and then correct your models and go back and forth. And I think in this school, it was kind of the spirit of that was very nicely reviewed in the lecture by David Gross. But students attending here, not only students, may have a feeling that we are roughly 50 years late to proceed the subject in this way. So kind of, I'll try to convince you that there is still something to be done along these lines. I'm not sure how can we can still do model. Right. Yeah. But well, I think it's more fun. This going back and forth with experiment is more fun, at least for me personally, or maybe don't feel myself strong enough to solve all the models which have to be solved in this case. Well, and at least one corner where of the theory where I think this kind of activity is still possible is related to the question which was nicely reviewed in the talk by Ed Witten, that, well, essentially experimentally, where by experiments here, I mean both real experiments now and simulations, we know that QCD is a theory of strings. And the question is, can we understand these strings? And at least in the way I will be approaching this question, unfortunately, there is no hope for $1 million prize because many of the lectures here, I think they were approaching confinement and from different side. So when you start from field theory and trying to prove confinement, and that would get you to $1 million. But here I'm taking confinement for granted, and hence I'm taking the existence of strings for granted. And I'm trying to start from that direction and understand those strings. Of course, well, if one follows that path and eventually derives QCD back from string theory, well, from that theory of confining strings, that maybe there is a chance, but it's a rather distant chance. But still, I think it's an interesting question. And again, as was emphasized in Ed's talk, the natural starting point is take NC to infinity. So that's where the string theory is weakly coupled. And well, in what I will be doing, it really, what I mean by infinity taken to infinity, I really will work in the limit when NC is strictly infinite, which means from field theory point of view, we're dealing with a infinite set of free particles, hadrons. So one may wonder what is there remains to do apart from understanding maybe the spectrum of these particles, and that's a key question. But really, I think there is an even more basic question, and namely understanding. So from the fact that QCD is a string theory, we expect that these particles should be excitations of some bullshit theory of a string. So the question is to understand dynamics of that bullshit theory. Well, there are, again, different set of observables to focus on. And here I will be guided by a piece of data coming from Lattice. And well, there is also natural theoretical reason to look at this, but my primary motivation, at least initially, was thinking about Lattice data. And this is what Mike mentioned, but I'll talk about it in more detail. But the kind of data which I'm looking at here is that one, well, thinks, because Lattice is always on a compact Euclidean space, but here I'm thinking about it as three dimensions being much larger than remaining one. So I'm thinking about geometry, which is R3 crosses 1. And then the set of data is that one may look at the 2-point functions of two Wilson lines, so Polakov loops which wrap around this compact circle. And of course, because it's all Euclidean, then it doesn't really matter which direction to consider as time or which in space. But for the purpose of interpretation I have in mind, it's helpful to think about this as a time direction. So it's a Wilson line which wrapped around circular spatial direction. And so one looks at the correlators of this kind, where all is trace of path ordered exponent of the gauge field, and mostly for what I will be talking about, this trace is taken in the fundamental representation, although there is also data about other ones, but for the purpose of these lectures, we'll be mostly interested in the fundamental representation. And now, as Mike explained in his lectures, so what one measures this way is the following. So this correlator, one may think about this correlator as a sum of exponents, where what appears in these exponents are the states which are produced by a single Wilson line. And so what kind of states these are? Well, as soon as the size of this circle is sufficiently large, and that will be always the case in what I will be doing, and sufficiently large means that they're what's called center symmetry, and in kind of more modern language is the zero form part of the one form center symmetry, which is associated to the presence of this compact circle. As soon as center symmetry is unbroken, this operator, which wraps once around the spatial circle. It carries charge under that center symmetry, and hence the states which will appear in the middle, they will all schematically have the form. They will have the feature that they should have a string wound around this compact circle. But of course, there could be kind of something else, right? So in principle, there could be additional closed strings which are topologically trivial, which may contribute here, and all the states, they have the same charge under center symmetry. And so just as a matter of terminology, so what I call long string, it's really, it more or less corresponds to winding. So when the string is wound around compact directions, that's what I mean by long, having in mind eventually considering the limit when the size of the circle is very large. So then actually there are two interesting regimes when one may consider here, namely one regime is when the energy which we're looking at and the gap between that energy and the ground state energy of the ground state of a string which wrapped around the circle is smaller than the gap of the bulk theory given by the glue ball mass. So one may either consider this regime, or one may consider a regime where there is no limitation like that, but taking large NC limit. So in both cases, the contributions of this additional closed strings are not there. In the first case, just purely kinematically, so there is just not enough energy to produce glue ball in the bulk. And in the second case, because kind of this kind of states there correspond to multi-trace operators, which don't mix with single trace in the strict planar limit. And so in both of these regimes, what these observations provide for us, they provide these energies, and these energies, these are finite volume energies of a Wolchit theory of a string, right? So yes. No, I'm kind of, if one just looks at the states which are lower than the mass gap. So here what I mean, so in principle, by doing this kind of measurements, one can determine, well, as many states as kind of computer power allows you, and if one restricts to the states which are below the mass gap, those states, they're just pure string excitation. Right. Right, that's why I subtracted is 0, right? So both ground state energy and excited state, they both. No, because this proportion, basically this theory has vacuum energy, cosmological constant, but that enters both in E0 and En. So the part which is classical part, which is proportional to the length, will be the same for ground state and excited states. That's why I'm looking at the. Right, that's what, but in principle, one just looks at all excitations, but there is subset of excitations which have that property. And kind of what I'm saying, that those excitations, those we can think about them as a finite volume spectrum of the Wolchit theory. Right, but physically, yeah, there are some local excitations on the long string. And well, and in the large NC limit, just the large N suppression separates for us two sectors, and the multi-trace excitations can be dropped. So, well, and kind of really from practical point of view, that's what we want to understand. We want to describe data which Mike with collaborators obtained about this finite volume spectrum. But from that perspective, it's already kind of clear if you ever studied field theory and try to look at the finite volume field theory. Well, finite volume field theory is more complicated than infinite volume field theory. So it's good to first consider then the limit r to infinity. And in the r to infinity limit, what we have a kind of, we study single infinitely long string, which stretches through all of the space-time. And next time we see that this limit is not only kind of simpler, provides us a simpler setup, but actually provides kind of thinking about that limit first, also provides the powerful theoretical tool how to properly organize finite volume calculations of the finite volume spectrum. But for now, we can just think, okay, that's to some extent also from purely theoretical viewpoint. If you want to understand dynamics of a string wall sheet, that may be the simplest background to consider. That's not kind of, at least in string theory, that's not what historically was done, but that looks a very natural starting point from a number of perspectives. And while thinking about this, well, if we think about this infinitely long string, then the natural observable to consider is the wall sheet S matrix, namely, as Misha said, the excitations of the string. You may think about them as kind of local bumps on a string, and because string is infinitely long, there is infinite region, and so if we're doing field theory, the kind of one of the first and most basic observables to consider is what happens when you consider scattering of these bumps, and there are three regimes which are useful to think about. So regimes is first, which roughly corresponds to kind of what I was talking about here. It's not exactly the same, but morally it's closely related, is that energy is, well, like smaller or approaching the string length. So like in some number of previous talks there, string length for me, that's, well, in case of QCD, that's the same as lambda QCD. And by the way, I should have said that given that I'm thinking about large N limit, for me, QCD is just synonymous to Purian-Mills. So string length is for the lambda QCD. And also that's, it's set by the tension of a string. And so for excitations, for like collision energy of these bumps satisfying this condition, we will see momentarily there is we have a weakly coupled to the effective field theory. So that's in some sense the most straightforward, but tractable and already interesting regime to consider, as we'll see. Then there is yet another regime, namely, if we consider energies kind of above tension of a string, and as we'll see momentarily, so this weakly coupled effective field theory at these energies, it's a power counting non-normalizable theory, which means it gets strongly coupled at large energies, and these what large means here, it's exactly that tension of a string sets that scale. So in the regime, in this regime, we now get strongly coupled theory. But what the presence of large N buys to us is that it's still 2D wall sheet theory. So namely, Naively, if there is no additional parameter, one may think that when you consider scattering of two bumps on a string, the moment the excess energy or collision energy of these two bumps is enough to produce glue balls, as a result of the scattering, string may self-intersect and kind of give you a state like that. But this probability of this process is suppressed at large n. And one may do some simple kind of dimensional analysis, basically to estimate kind of if you have two excitations like that, the estimate one roughly goes along the following line. So for a string, the excitation energy is proportional to proper length of the excitation of the segment of a string. And then one may estimate the number of self-intersections which you obtain as a result of this collision. And kind of it's easy to convince yourself that this the dominant number of self-intersections will come from short string segments. And then so this estimate for the upper boundary of this region comes from requiring that the excitation is large enough so that you have of order n squared excitations, because the probability of this process, so the probability of string pinching goes like 1 over nc squared. So based on that, one can estimate at what energy the glue ball production becomes unsuppressed, and that's where the scale is coming from. And so that this regime, to me, that's what really makes QCD string interesting, and kind of more interesting than some garden variety string like, well, say shoelace, right? So normally what would expect that the moment you cross the tension scale, you lose 2D theory at all, and there is no separated to the sector, but the presence of large NC, this additional parameter, buys us the presence of this additional regime. Right. So while in real world QCD, while in C equals 3, so this number is maybe like 1.5 GeV, or it's not that high. But also one should have in mind that kind of in this kind of estimates, one may have some like there's some factors of pi lurking around, so it may be actually better than it looks. But of course, also in the real world QCD, the complication is that we also have 3 flavors of fundamental fermions. I think that's actually a bigger problem than to kind of describing it with a string. Yeah. Well, and finally, there is a third regime where, well, E is larger than the scale, and C ls minus 1. And in this regime, really, there is no well-to-do separation between 2D worldsheet theory and the bulk theory. They strongly mix with each other. And kind of my analysis will be always either restricted to this regime, or, and that's I think the most interesting really set of questions, is that one considers the limit when first takes E fixed, energy fixed, and takes NC to infinity, then kind of this third region taken to infinity. And this way, one obtains UV complete 2-dimensional theory, which decouples from all the rest. So there is often kind of this attitude that QCD flux tubes, well, that's also kind of the name suggests, they're not actual strings. They're not as fundamental strings, because they're really intrinsically effective field theoretic objects. But thanks to the presence of this additional parameter, that's not quite the case. So by taking NC to infinity, one can really obtain 2-dimensional subsector, where one can now ask questions about scattering at arbitrary high energies. And I think that's what makes it interesting. Yes. Well, we'll connect this to, so far it was just like a motivation, right? We started talking, okay, lattice provides for us measurements of finite volume spectrum of the wall-sheet theory. But before talking about finite volume spectrum, let's discuss the simpler question, how the infinite volume theory looks. But in the next lecture, we'll see that actually this viewpoint also practically turns out to be very useful in terms of obtaining predictions for finite volume spectrum. Actually, that's the most, turns out to be that the most efficient way to obtain predictions for finite volume spectrum by first calculating the scattering and then going from S matrix to finite volume spectrum. But for now, you're right. So kind of that was a motivation, but now we can forget about, for some time, we can forget about finite volume spectrum. Okay, good. Are there any other? Sorry? Well, they're not that far apart. So there's a roughly factor of roughly factor of 2 to like 3 between them. So the lightest global mass is like 1.5 GeV, and the string tension maybe like No, in the larger limit, both LS and global mass, they're both fixed. So that's, or maybe I'm not misunderstood. Well, parametrically, they're all the same. So there is the global mass, it's for the LS minus 1, and is for the lambda QCD. So parametrically, they are at the same scale, and there is kind of the top limit is designed essentially in such a way that these quantities stay finite. Why it's not, sorry? Yes. Yeah, that's the whole point which I'm trying to make here. Yeah. So in this second regime, indeed, I'm taking energies larger than the global mass in the bulk. So kinematically, when I can see the scattering on a string, there is enough energy to produce those globals. But thanks to 1NC suppression, this production is still small. So my theory, even though kinematically I can produce extra states, the theory is approximately unitary, and that was because the estimate which I referred to of the scale, it's where this probability of global production becomes order 1. So it's suppressed at small energies, but it goes order 1 at this scale. And so if one takes NC to infinity first, then one gets a theory on the volt sheet which is completely decoupled from bulk excitation. So I think maybe it's helpful to make an analogy with critical strings. So in the critical strings, that corresponds to something which sounds very boring. So we have alpha prime, of course, but then we have G string, and I consider the limit when G string is exactly equal to 0. So if I have infinitely long string and can see the excitations of that on that long string, then nothing happens in terms of they don't produce extra strings in the bulk. So what's usually called string S matrix, it's completely trivial, but we'll see that there is still some non-trivial dynamics which stays even in this limit. Did I answer? Any further questions? Okay, so if not, well, I should actually, there are a couple of comments to be made here already, and we see some glimpse why the problem of understanding this. So the problem is really understanding kind of volt sheet theory in this regime, including this strongly coupled region. That's what I mean by when I say that I want to understand the theory of confining strings. This is the first step. So for instance, we had a nice set of lectures by Mitad where he identified this regime when kind of one can study confinement by using weakly coupled methods. And essentially it's my understanding that all these considerations, they can work in this regime number 3, because the theory was in that setup. The theory was weakly coupled when the circle size was smaller than well, exactly this parameter, and that's when the dynamic was strictly coupled. So even though, as Mitat argued, there is no obvious order parameter separating that regime from regime of the large circle, from the point of view of these considerations, it's not immediately clear how that weakly coupled analysis can help us. Also, if there was already some review of ADS-CFT, this tells us that ADS-CFT in the regime when we have a supergravity description, again, is not the right thing to consider, because that regime assumes that the curvature of the bulk space should be long compared to the string scale. So most of the so in other words, most of the excitations which you find in that regime are really KK modes of graviton or as other bulk fields, but not the genuine string excitations. And in actual young males, we're interested in the regime when all these parameters of the same order. So from in ADS, it doesn't mean that ADS-CFT won't be eventually useful, but it just tells us that we really need to think about some strong curvature regime. So from that point of view, this kind of study, numerical study of Young-Mills theory is experimental, corresponds to experimental study of some strongly curved string background, which I think is very interesting. Okay, so let's say now a few more words about this setup. And well, actually, in model building, it's always good to start with some question. And for me, I think the very interesting, like this, that was a question which dragged me into this building, into this field. The question was the following. So we have this regime where we can talk about long strings. Either they can be weakly coupled. We can even start with really weakly coupled case. So for now, let's consider this regime E much larger than ls-1. And momentarily, I will describe for you. So I told you that it will be weakly coupled to the effective field theory description. Momentarily, I will review it for you. But the question is, well, we know from string theory textbooks that something happens when something special should happen when the string lives in 26 space-time dimension. And as we'll see now, in principle, at this level, I will be able to write this weakly coupled effective theory in any number of dimensions. So let's in the remaining part of today's class, we'll see the question which we'll address. It's what is special about d equal 26 if I'm naive effective field theorist who doesn't know any of the string theory. And that's roughly who I was like 10 years ago. And I look at this effective field theory. When is the first time when I notice that something interesting and special happens when I consider this long string in 26 dimensions? So to address this question, so let me, oh, there's something here, but I can erase it. So let me now review how effective field theorist would describe a system like this. So one would describe it in terms of symmetries, namely the presence, so the full, we started with the theory which is Poincare invariant. And the presence of this long string background results in spontaneous breaking of this Poincare symmetry into two-dimensional theory, two-dimensional Poincare symmetry along string bullshit times rotations around the string. And so in this case, we know that the low energy dynamics will be described by dynamics of Goldstone modes. call this also known xi's, where here I is equal to all the way to d. So I'm thinking about string which is stretched in the first direction. And these are just Goldstone modes of spontaneously broken translational symmetry.
Why is the setting as string spontaneous and not explicit?
Well, because it's a state in my theory. I didn't the level the string which I have is just an object on my theory. It's in the same way like I'm breaking by my presence here. I'm breaking Poincare symmetry by selecting preferred reference frame. So in the same sense, this background. So the interaction dynamics is still Poincare invariant, right? Poincare symmetry is present, broken due to the presence of this background, which I consider here. As was already mentioned, I think in Nati's lectures, so this is one of those situations when the number of Goldstone modes doesn't match the number of broken generators. So here there are broken generators corresponding to translations, and that gives rise to this d-2 Goldstone bosons. By the same Goldstone bosons, they also ensure that the theory is invariant under nonlinear realized boosts. So that's a classic example when a situation like that happens. And well, actually, also this is confirmation of one other thing which Nati said, namely that there should be counterexample with like sufficiently relax some of the assumptions. There should be counterexample to every statement which he makes. So here, no, we're doing something very unusual here. We're discussing system of Goldstone bosons in 2 dimensions, right? Because they're the system which have like bullshit theory is 2-dimensional. So from the point of view of effective 2-dimensional theory, these are all global symmetries, and these Goldstone bosons, I'm talking genuinely about spontaneously broken system with spontaneously broken symmetry in 2 dimensions. And well, as far as I understand that there is nothing wrong with Coleman's paper apart from the title. So so this will be, as we'll see momentarily, this will be genuine really system of interacting Goldstone particles in 2 dimensions whose interactions governed by nonlinear realized symmetry. But there is no other parameter here because, well, if you look at low energies, well, you'll find just a system of free bosons, for instance, is essentially what Coleman has proven in his paper is that operator xi is not well-to-do operator. But to describe this particle, I don't ever need to talk about xi. It's enough to think about derivatives. Well, but we'll see. Because I think part of what I will be doing, I think part of why it's fun is we'll see that one really can run all the machinery of Goldstone bosons applied to the 2-dimensional system and get something interesting out of it. Okay, so these are my dynamical degrees of freedom. Well, and in general, I don't expect, unless there is some additional symmetry in the system, I don't expect to find any additional massless modes. So if I go to sufficiently low energies, that should be all what it is there. And we'll discuss next time this is confirmed by lattice simulations of Young-Mills. So indeed, if you look at the confining strings in Young-Mills, then there are no additional massless modes present on the whole sheet. And so to build effective field theory describing dynamics of these modes, well, it's convenient to look at the object, which is d-dimensional vector. So you may think about this as analog of, say, U field in chiral pi and Lagrangian, or you may think about starting with kind of more covariant description of a string and fixing what's called static gauge, x0 equal tau, x1 equal sigma. But from this effective field theory viewpoint, it's kind of better to kind of right away work in the description when all the degrees of freedom are manifestly physical. And these are these transverse modes. Well, but the rest is pretty standard. So to build the most general the most general action describing this weakly coupled regime is just a local action build of geometric invariance, which one can construct out of this data. Namely, there is a induced metric, which you define in the usual way, and then so the low energy dynamics of these Goldstone modes is given by general action of this form. So the first term is just Nambu-Goth action. So that's how I define my string tension. And then in principle, one may write kind of all possible geometric invariants, like R plus beta R squared, where this R squared, these are this is the curvature, intrinsic curvature of the voltsheet. It's a curvature constructed of the that correspond to that induced metric, but also one can write geometric invariants like this, square plus etc., where K is an extrinsic curvature tensor. And this is my effective field theory and all these high dimensional operators. So if I go to low energies, then dynamics is governed by Nambu-Goth action plus correction, plus a set of corrections. So there is something very interesting which happens in this theory. So first of all, this is a theory, like low energies, it's a theory of interactive massless scalar fields. And when I was starting to thinking about that, and that related to this Coleman, Merman, Wagner argument, kind of we used to be scared of interacting massless scalar fields in 2 dimensions. So the expectation was that if I was to start calculating scattering of these modes, that there will be some bad IR divergences. But then you just start calculating and you find none. And well, there is a simple reason for that. But most technical level is basically the point that in this action, every field is hit by derivative. And that's enough to eliminate IR divergences. More kind of advanced argument says that, well, IR divergences kind of the most associated with situations. Well, basically, one thinks that it's hard to define S matrix for massless particle in 1+1 dimension, because if you have kind of particle propagating with speed of light in some direction, that is impossible because there is no directional information which may use. So there is no way to separate wave packets. You have one particle or several particles propagating with speed of light in the same direction. They never separate. So technically, it corresponds to, if one looks at the scattering diagrams, then one may say one has some right mover, and then one may worry about splittings when one right mover splits into 3 right movers, say, and that may lead to IR divergences. But what happens in this situation that our theory at very low energies, it's a free CFT, it's a theory of free bosons, which is perturbed just by a set of irrelevant operators, which means that if you consider just a bunch of right movers, and on one hand side, you may apply large boost to them and to make the energies very small. And because of Lorentz invariance, that doesn't change the scattering amplitudes. But on the other hand, because all interactions between these particles, they're all irrelevant, but making this boost larger and larger, meaning making these particles softer and softer, the interaction goes to 0. And that eliminates the presence of higher divergences in the system. So there is a well-defined S matrix. And one may go ahead and start calculating it. So I remind you again, the goal was, the goal which we posed, we want to find a place when d minus 26 will show up, when we'll see that something special happens in this description when number of space-time dimensions is equal to 26. And so in principle, we set up the system. We can just go ahead and brute force calculate what happens here. And that's initially what we did. And the result is quite interesting. So I describe it later in slightly different language, but I think it's instructive right away to give you the answer. So first you calculate 3-level diagrams, right? So here, which means that the low energy amplitudes at the leading order in the LS expansion, they're just given, low energy expansions, they're given just by the leading Nambu-Gote term. So you start calculating interactions associated with Nambu-Gote. So there is some non-trivial 2-to-2 scattering. So these are flavor indices of this of my particles, and one finds amplitude, the leading amplitude of this form squared O2 delta IK delta GL. So it's very simple. So it tells that actually there is no annihilation term. So in principle, general OD minus 2 invariant amplitude could also have term proportional to, say, delta J, delta KL. But that doesn't happen in Nambu-Gote. So there is only pure transmission, and that's the answer which one get. But then one, in principle, one can go further. It becomes actually quite fast. It becomes quite laborious, but in principle, one can do it and start looking at the multi-particle scattering. And one finds that the theory is integrable. Namely, there is a cancellation. So roughly speaking, as I say, level of 3-to-3 scattering, there is a cancellation between this kind of diagrams and this kind of diagram. So, so remember what I'm doing, all my interactions coming from that square root of that G term, right? When I expand it, it starts with dx squared, then there is dx to the 4, dx to the 6, etc. So there is an infinite series of interaction vertices. And what happens in this model that's similar how it happens, say, in Sine-Gordon theory, there is a cancellation between 3-level amplitude with 2 4-particle insertion and with 6-particle vertex, such that there is no connected multi-particle S matrices. So the multi-particle S matrices at the 3-level, they're just given by products of 2-particle scattering, right? And that's what in 2-dimensional context, that what one calls integrable model. So there is no particle production. So that's what happens at 3-level, and later we'll see how to kind of derive this in a better, more efficient language than just doing this brute force calculation. Well, and in general, effective field theory, that would be more or less the end of the story in the following sense. So let's compare it to the, say, theory of the Cairo-Lagrangian describing fine interactions. So there it's a theory in 4 dimensions, so that low energies is described by this leading term, and similarly to how it happens here, all 3-level interactions fixed by this leading term. But then there are high dimensional terms, and so schematically, like say, with extra pair of derivatives and with undetermined coefficients. And the moment one starts calculating loop processes in this theory, there will be also contributions with some free coefficients coming from these high dimensional interactions here. And so as one goes to higher number of loops, meaning higher order in derivative expansion, one gets more and more parameters. Well, in principle, the same is true here. But something interesting happens in this system of Goldstone bosons. Namely, if we look at the next to leading order, the what corresponds to one loop scattering with a leading Nambu-Goto piece of the action. So what kind of counter terms we may write? So there is this term which I wrote here. Then could be K alpha. Well, actually I wrote it over there. There is this term, and there is also K alpha beta I squared. So different contraction of indices. So it's easy to convince yourself that at the next to leading order, there are three local terms which one may try to write. But then what happens is that first there is a relation between these three terms, thanks to Gauss-Kadatz equation. So these three geometric invariants, they're not independent. So there is a relation to that. And then this term, it's total derivative in two dimensions. So it doesn't contribute to on-shell quantities. So everything is reduced just to this term. And this term can also be written as box xi squared. So it vanishes on shell. If one imposes leading order equations of motion following from Nambu-Goto action, then this term vanishes, which is equivalent to saying that one can always do field redefinition and remove this term. So what this counting tells us that in this theory of Goldstone bosons, not only tree-level amplitudes, but also one loop amplitudes, they're completely fixed by the leading order classical action. So that's kind of peculiarity of this system of Goldstone bosons as compared to, say, system of Pines. Of course, if one goes to higher order in loop expansion, they're pretty similar. So then one starts getting higher the coefficients. And for instance, at the there are two trivial operators which one may write to next to leading order, which is basically can be, well, one of them can be written as R squared, or alternatively just some K to the 4 operators. And I think they will play some role in what Zhao is going to tell you later. But at the level of one loop scattering amplitudes, there is nothing, which means that one loop scattering amplitudes, they are completely determined by Nambu-Goto action. So in principle, if you are have enough patience, you may go ahead and calculate those one loop amplitudes, and it turns out that to be useful. Namely, for instance, for 2 scattering amplitude, one gets the following answer. So it's again Mij KL. So there is some tensor structure. So there is a essentially that was their tree-level piece, and then there is which is pure transmission, and then there is a piece which is fixed by unitarity, which appears here. So there is that part, but in addition, there is one finds that at one loop order annihilations appear, and so the answer cube delta J delta KL, and well, the rest can be reconstructed from crossing symmetry, but let me write it down. Delta K. Actually, it will be, I will need explicit expression momentarily. Plus U cube delta IL delta JK, where ST and U, the usual Mandelstam invariants. Well, and most importantly, the price for doing this calculation is a prefactor here, which is d minus 26 over 192 pi. So we see d minus 26 to appear. Well, it may be not immediately clear the significance of this from the 2 scattering amplitude, but one can work a bit harder and calculate also now 2 scattering amplitudes. So what happened at 2 level that, so remember 3 level this matrix was just transmission. Now there is also annihilation term and a reflection term. But if one look at the now kind of the diagrams like this, for instance, for 2 to 4 scattering, one finds that there is also contribution proportional to d minus 26, which is non-trivial and connected. So that means that in this theory, so at least that kind of effective field theory's answer to what is special about d equal 26, that at the classical level, this theory of Goldstone bosons has a special property. It was integrable. So in addition to Poincare, non-linearized Poincare symmetry, there was a large additional symmetry, which essentially the particle numbers of all individual Goldstone bosons were conserved. And that symmetry, because this one loop calculation is universal, there is no counter term which you can add to the theory to cancel this. So this calculation tells us that if d is not equal to 26, that if one quantizes the theory consistent with Poincare symmetry, as we want to do because we're thinking about QCD strings, the theory which gives rise to these dynamics is Poincare invariant, then necessarily the theory will be non-integrable. By the way, this argument makes very precise another point which Ed made in his talk, that we should somewhat temper our expectation of how large we can achieve when we think about Lagrange-Yang-Mills theory. So if we see that if we consider d equals 4 Yang-Mills, so this argument, well, assuming there are no additional states, massless states on the, so the only ingredient which goes in here is the fact that there is a string state, so the pattern of symmetry breaking, and assumptions that there are no additional massless states on the string wall sheet. In QCD, we don't expect to find any, but in principle, maybe a miracle happens. So one should go and check, say, using lattice data, and lattice data quite unambiguously shows that there are no additional massless states, importantly, also in Lagrange limit. And so the moment we have these two, we know that even if we take strict soft limit, even if we work in the strict infinite n, there is dynamics of the string itself is described by two-dimensional theory, which is not integrable, which means, well, there is particle production here, which in practical terms, I think it more or less means that it's hopeless to kind of solve planar Yang-Mills in the same way as it, for instance, happened for n equal 4 super Yang-Mills. And we'll discuss later. So that definitely raises a question, kind of what are we doing here? So what is the goal? So one should be careful in asking a correct set of questions here. But that's kind of already important conclusion, which one gets from this calculation. Well, actually, one point which will be important later. So there is a caveat to this argument at d equals 3. So if one looks at this prefactor, nothing special happens at d equals 3. But now if one looks at this expression here, so we have a single flavor. So there is only a single channel here. So this amplitude reduces to s cube plus t cube plus u cube. And in two dimensions, two-dimensional kinematics is such that either s is equal to minus t is u equal to 0, or s is equal to minus u and t equal to 0. So this factor always vanishes in d equals 3. And similar cancellations, they persist for higher order amplitudes. So all these non-universal amplitudes, all these universal amplitudes, they actually vanish at d equals 3. So in principle, there is a room for integrable dynamics on the wall sheet of d equals 3 string. I should say right away from, again, from lattice data, we know that's not the case. We know that in Lagrange limit of planar Yang-Mills, this finite volume spectrum, which one observes on the lattice, is incompatible with integrability at Lagrange. But this theoretical argument is not enough to come to this conclusion. And also, still, this observation will be important later on. So in the remaining time, how much do I have? Like, yeah, so lattice data in 3 dimensions, just this finite volume spectra, which one finds from and extrapolates at large N, they're incompatible with integrability. So we know experimentally, even though based on this argument alone, one may think that maybe large N limit of 3D and Mills in 3 dimensions could have been integrable. We know experimentally that's not the case. How much time do I have? Huh? 15. Okay, good. So in the remaining time, instead of doing this one loop calculation, I do a couple of exercises, which kind of, I think they're fun from the viewpoint that illustrate that really we can work with this system of gallstones in a way how we usually work with gallstones without doing explicit calculations, but using current algebra technique. But also there will be a benefit of doing that will actually, so far the analysis which we had so far, so we said like conclusion which we draw that if D is not equal 3 or 26, that means 3-level integrability is broken necessarily, but at D equal to 3 and 26, in principle, it looks like there is a room to construct an integrable model. So one may ask the question, well, if such a model, whether such a model exists, and if it exists, what is the corresponding S matrix? And what I will do now will give a derivation. So we'll find the corresponding S matrix of the corresponding integrable model, and somewhat not surprisingly, at D equal 26, this will correspond to S matrix on the whole sheet of critical strings. So if you wish, kind of all this line of reasoning provide for you kind of alternative historical scenario of how critical string theory could have been discovered if these were not like smart string theories, but kind of effective field theorists were thinking about this question. They would arrive to the structure along this path. Okay, so let's think what are the consequences kind of. So what we'll do analysis similar to what one does in deriving soft theorems for pions. So what are the consequences, general consequences for nonlinear, for these scattering amplitudes of Goldstone bosons, which one expects from this nonlinear realized symmetry. And so the argument kind of pretty standard. So first of all, there are nonlinearized translations. So there's a conserved shift current, this theory, shift current, which is associated with translations xi going to xi plus constant. And schematically, this shift current has this form, d alpha xi plus s alpha I, where I separated two pieces. This is a linear piece in the Goldstone boson, this linear piece in X, which is this term is responsible for this transformation rule. And so this term is nonlinear in my fields. And then to derive soft theorem, one starts with this equality. One considers the matrix element of the divergence of this current between two arbitrary on-shell states, and that following what is written here, that can be written as p squared times matrix element of the field X plus p alpha times matrix element of the nonlinear part of the current. So that that should be equal to 0, and which tells us, so now this term in the limit, now if I take now on shell limit, so far I didn't take, I was off shell, but now I'm taking on shell limit when p squared going to 0. So this limit produces for me the, so there is a LSZ pole here associated with this Goldstone boson. So I get relation of this kind now, depending on whether P0 is positive or negative. This, I have extra particle in initial or final state. And so this kind of on shell amplitude is equal SP alpha initial. And now, because this is nonlinear operator, the standard argument goes that this nonlinear operators, there is no singularity here. There's only z pole here. So there is no singularity when p squared goes to 0. So from here, we conclude that this kind of amplitude is solved in the limit when the momentum of a Goldstone goes to 0. This is identical to derivation of the soft theorem for pions. Well, and actually in this case, it's clear overkill because unlike in pions, in these Lagrangians, there is a derivative sitting on every field X. So this soft theorem is completely obvious from the grammatic point of view. It's not obvious for pions because there are interaction vertices like where you have d pi squared and pi to arbitrary power. So there is no derivative sitting on every pi field. In this case, for this system of Goldstone bosons, this soft theorem is completely obvious, but it's a good sanity check. No, that's wrong. This is a counterexample. I already said the derivation of Coleman's theory is correct. The conclusion is wrong. What theorem proves that there is no operator, there is no other parameter, there is no operator X. One may be a bit worried here because kind of here it appears, but perturbative theory view, but the Coleman made a conclusion based on this argument that there are no interacting massless Goldstones, and this is a counterexample. So this is honest to God counterexample to the statement that there are. Right, the theorem is that the two-point function XX. Right, but I don't to define the scattering amplitudes of these Goldstone bosons. I never need to look at the correlators of X. It's enough to look at correlators of DX and extract from them the scattering amplitudes. So the theorem, kind of what it's proven is proven that there is no well-defined operator like that in free field theory. And this is different statement from the statement that there are no interacting Goldstone bosons. So kind of to some extent, as I said, this exercise was meant to have some fun, exactly to illustrate this point. So this is a genuine counterexample to Coleman's theorem in the sense that it's system of interacting Goldstone bosons in 2 dimensions, whose interactions are governed by non-linearized symmetry. There is non-trivial S matrix, which is well defined. There are no error divergences, and the properties of this SSS matrix they're governed by word identities of non-linearized symmetry. In particular, that's where this d-26 factor came from. Okay, but so that's kind of one first order exercise, but of course, this is an overkill. And actually, we'll see momentarily. So let's do something more interesting. Let's see the consequence of the presence of the non-linearized boosts. And we'll see in that exercise, we'll see that there is a price to pay for working with Goldstone bosons in 2 dimensions, although the price won't be that large, but something interesting happens. So let's first work out the consequence of the presence of non-linearized boosts. So, well, one starts with the same kind of logic. So there is a boost current. So that corresponds to a non-linearized boost in kind of beta is one of the two dimensions and I transverse dimension. So that corresponds to boost or rotation in the I beta plane. And we expect that current to have this form. So there is a part which is proportional to the shift current. So this is to say that's what boost is. But in principle, one may expect, so there could be some addition here, which is kind of some additional flavor rotation with no additional sigma dependence. And so in particular, for Nambu-Gotha part of the action, well, let me I'll illustrate momentarily what this is. But so this is the general form of the boost current. And now if one imposes conservation of the boost current, one actually learns something new about the shift current, which is not that surprising. That's why the same Goldstone boson in this case plays dual role. It plays the role of non-linearizing both shift and boost symmetry. And from saying that this is equal to 0, one learns that, well, when derivative hits S, it will be 0 because shift current is conserved. One learns that shift current itself is a derivative of that part, well, of this nonlinear part of, well, this additional part of the boost current. And for instance, in kind of this operator K, so in the case of, say, Nambu-Gotha from leading order Lagrangian, and that will be actually important momentarily, it's delta alpha beta. Right, plus xi t alpha beta plus etc., where this is a energy momentum tensor of d minus two bosons. So with this extra knowledge, we can look at this relation which we had here, and we conclude that, well, on the right hand side, because this S here is itself a derivative, we conclude that actually this on-shell amplitude is not just soft, but it's double soft. Namely, there is additional kind of, I write this as P times K, schematically dropping all indices. And so I find that the on-shell, well, here, it's better to look here actually. So schematically, I get relation like this. I find that this on-shell amplitude is not just soft, but it's doubly soft. Well, and that's not that surprising. So roughly speaking, because boost can be thought of as shifts which are kind of modulated by linear function in X, and the theory should be invariant also under this kind of transformations. And that I think that was something to expect, that on nonlinear boosts they translate into double soft properties of the Goldstone amplitudes. But well, given that we're somewhat worried about the system by the reasons Misha referred to, so it's kind of a system of Goldstone bosons in 2 dimensions, it's good to go and check whether that soft theorem holds or not. And it turns out that if one looks at these universal one loop amplitudes which were obtained by direct calculation, they actually violate this double soft property. So this is the price to pay for working with Goldstone bosons in 2 dimensions. I think I ran out of time, so probably. Okay, so I was planning to explain to you in more detail what happened, and that will allow me to derive that integral West matrix. But probably it's better to postpone till next time. So far the bottom line that there is this soft theorem which holds for scattering of Brownians in high dimensions. So if you look at the scattering of, say, Brownians on 2-dimensional membrane or 3-dimensional membrane, they will all satisfy this property. They will be doubly soft. For a string, there is a violation of this double soft property, but we'll see next time. One can understand diagrammatically where it's coming from, and that will allow us kind of essentially by requiring the cancellation of non-double soft part of the amplitude will allow us to uniquely reconstruct the integrable S matrix. But we'll start with this next time. Yeah.
Thank you for very nice talk. Questions? Yes.
So you mentioned that there is evidence that D equals 3 plus Yang is integrable. No, it is not. It is not integrable.
So what I said is that these arguments, they provide a no-go for the possibility of integrability in D equals 4 at large n. At D equals 3, there is still a room. And indeed, we'll see later on, there is a potential integrable model, but just lattice data shows that's still not the option. So lattice data. Well, it's both for from global spectrum and actually from the flux tube spectra. Just the finite volume. That's kind of preview what we'll do next time. So by using this finite volume data, one can get information about this bullshit S matrix. In particular, at D equals 3, one finds that there are corrections which are incompatible with integrability.
So if I understand correctly, in the continuum, you cannot rule out the possibility that the D equals 3 is integrable, because the lattice is indeed ruled out.
Well, no, the statement is in lattice. I'm using just as an experimental input, but all the statements which I'm making are in the continuum. Just at D equals 4, one can rule out this integrability just based on the low energy effective series calculation, assuming IR asymptotic of a series, that there are no additional massless states on the bullshit. So these arguments are not powerful enough in D equals 3. But all the statements which I'm making, they are in continuum, but using lattice as an input.
So here you're using this argument with this conserved currents in impractical theory language, but these local operators, they don't really exist, right? Because this is a theory of fluctuating geometry, so you can define as matrix, but there are no real local operators.
Well, they are being right. Yeah, so that's true, but it's not obvious from the get-go. But that's, I think, again, that's we'll see from that S matrix, which we'll see it has this property. But also, I think what Zhao is saying, I think that's another reason why confining strings are very interesting. So this UV complete theory, which we get by taking large n limit, we expect it to be not a conventional quantum field theory, but we expect it. It's a theory of fluctuating 2D surface. So one expects it to be something more like a theory of 2D gravity. Well, better to say it's not a completely local theory. And indeed, I think there are good reasons to think that there are no well-defined local correlators in that theory. But, well, you may think about it in different ways. It's kind of, these arguments, strictly speaking, they just govern the properties of perturbative amplitudes. But usually one expects that they extend to non-perturbative level. But for instance, this S matrix, which one derives this way, that defined non-perturbatively, and one may, and actually one can see from that S matrix already that the theory is not a conventional QFT at large distances. So, but strictly speaking, yes. So all what I'm saying here is a property of low energy expansion of these amplitudes.
But then since you take P to 0, the soft limit, then the conclusion will.
Yeah, but I think that's kind of the usual story with all these soft theorems. But one kind of wants to make a statement really about on-shell data, but in the middle, one uses the off-shell quantities, but at the end, one takes on-shell limit and update statement about on-shell data. I don't know how to do it better for soft theorems, but it's true. There is this caveat. Right? It's not completely on-shell argument.
If not, let's thank Sergei again.